other sheet of paper that I want you to have out is the one that's titled Polyatomic Ions, Compound Names and Formulas. So if you can have that out along with this sheet. And how about the periodic table as well? Quite frankly, from now on, I'd keep this thing with your periodic table. You might have a periodic table on the back side if you want to use that. If not, if you don't want to put back and forth, get out a different one. As you're getting that out, the top of this sheet says, to name a compound containing a polyatomic ion, simply list the name of the cation, followed by the name of the anion. For example, take the compound CaOH2, which is formed by the calcium ions and the hydroxide ions. Ca plus 2 cation is called calcium, OH minus is called hydroxide. Therefore, it's called calcium hydroxide. First, how do you know that you've introduced now polyatomic ions when you do your naming? The number of elements. All the naming we have done this year so far has contained 2 elements. Either a metal and a nonmetal, ionic, or 2 nonmetals, covalent. Once we get into 3 elements, calcium, oxygen, and hydrogen, realize you need to be looking at this sheet of paper to help you out. Because we are not going to call this calcium oxygen hydride. This OH is on this sheet of paper. It's hydroxide. So this will be called calcium hydroxide. If I look at the practice problem number 1, it gives me NaC2H3O2. Again, we would not call this sodium carbon hydrogen oxide.
Sodium acetate?
Acetate is the first polyatomic ion on this sheet. Notice that it's a -1 charge. That's why there's 1 sodium with the 1 acetate. If these are polyatomic ions, that means that they have a charge. And if they have a charge, they have to balance out charges when you write the formula. CuNO3. Again, we would not call this copper nitrogen oxide. We would look for, can we find this polyatomic ion there? Peyton?
Copper nitrate.
So, first off, copper is Cu, NO3 is nitrate. By the way, if you look directly above NO3 on this sheet of paper, you see NO2, which is nitrite. Very common that if you have an 8 version, the 8 version will have 1 less oxygen. There's a sulfate and a sulfite, a phosphate, a phosphite. This problem's not done, though. And the reason why this problem is not done yet is because copper is a metal with more than 1 charge. And because of that, we need a Roman numeral to represent what the charge is. Just like always, if we don't know the charge on the metal because there's more than 1 version, we do know the charge of the anion. What is nitrate's charge? It's on top of the column. -1. And if there's 1 nitrate, what must the copper be to balance that out? 1. Copper 1 nitrate. What I would like to do is have you, before we finish the rest of this now, flip to the back side of this. If part 1 on this worksheet is starting with the formula, give the name, just like any of our other types of namings, we have to go and do the exact opposite route as well. So I'd like to do the first 2 of these as well with you. then give you a chance to kind of work with each other on your own, whatever it might be. So we're going to do sodium hydroxide, bless you. Barium nitrate. And heck, let's do one more as a group as well. Oh, let's do number 5. Aluminum hydroxide. There. Sodium hydroxide. If you're given the name, you should be able to write the formula. Sodium symbol is Na. Here's the weird thing. On this polyatomic ion sheet, most of the things end in ate or ite. And that's a good indicator of, hey, this is the type of naming I'm doing. If it ends in ide, usually it's like nitride or oxide or fluoride, so it's just an individual element. But there is a cyanide, a hydroxide, and a peroxide all on this sheet. So most things that end in ide are just individual anions. There's a couple exceptions. Hydroxide is OH. Sodium is a +1 charge. Hydroxide is a -1 charge. They balance out to be NaOH. So this is a very important compound that we're going to focus on in our acid-base unit. Barium nitrate is the next one. What's the symbol for barium? Ba. What's the charge that barium has? +2. What's nitrate? NO3. And that should be a -1 charge, right? I cannot just write BaNO3 for the formula for barium nitrate because that would not balance charges. So just like you were taught before, we could kind of do that cross and drop method. However, notice that there's already a number at the end of here. When you balance formulas, you cannot change this into something else. But what we can do is put that polyatomic ion in parentheses and then put the 2 after. BaNO3, 2. Yeah.
When we're writing them, you want us to also write the charges at the top like you did for that second one? Or is it just...
To figure out your answer, it might be useful to do that. However, we need final answer. So this would be the final answer. One thing that some students do, and I'm not saying you have to do this, but some students, when they write the formula, regardless of whether or not they need a subscript afterwards, they like putting polyatomic ions in parentheses. That way they separate out the positive from the negative. We don't care in chemistry if you do that. If you want to do that, it's fine. Again, it's not necessary for NaOH. That's why I typically don't do it. But you had to use parentheses here, or else what would you do with that 2? It wouldn't make sense. And that's one of the reasons why I wanted to do aluminum hydroxide, which is number 5 on this sheet. Aluminum is a +3 charge. And once again, I know hydroxide is a -1. How would we write this? We could do the cross and drop, right? This is when I slowly walked away because I did something wrong. Max? Yeah, you're right. I need parentheses. There we go. Save me, Max. This is where I still did something wrong. The 3 has to be outside the parentheses. Because right now, how I have it written, I'm saying I have 1 oxygen and 3 hydrogens. But I need 3 hydroxides to balance that out instead. So that's why it had to be here instead. So again, we moved on to mole conversions. The good news is we don't change what a mole conversion is. Again, if you start with grams, you want to convert to moles somehow. And then you could convert to molecules if you needed to. You could do the exact opposite direction as well. What we need to focus on is this gram to mole or mole to gram step. Because remember, in order to convert from grams to moles, or vice versa, you need your periodic table because you need to figure out the molar mass of something. Does that ring a bell? So hopefully this is brief to show you how to solve for the molar mass, because then at that point it's the same type of stuff you've always done. So let's look at 2 problems, number 1 and number 7, on this sheet titled Polyatomic Ions Mole Conversions. And it gave you an example in the top of aluminum sulfate. But let's start off with the calcium cyanide. So what we're asking you to do on this front side is just figure out what is the molar mass. If you look on the periodic table for calcium, to the 100th place, because we like to read to the 100th place, what's calcium? 40.08. Now in calcium cyanide, there's also carbon. What's carbon? I'm letting you guys look it up, but Louis said I just have all these memorized. What's nitrogen? Ish? Oh, Max. We don't ish it here. 14.01. However, notice that there's a 2 on the outside of the parentheses, which means calcium cyanide has 1 calcium, 2 carbons, and 2 nitrogens. So what I can do is one of 2 things. Either I can multiply these numbers by 2, or I could have added 14.01 and 12.01 and then multiplied by 2. Either way, to solve for the molar mass then, I need to take 40.08 plus 24.02 plus 28.02. I actually don't have an answer key for this, so I'm going to see if I can do this. I had a little bit, but it's got to be a 1 then, huh? 12. 92.12 grams per mole? Right? People calculator? Okay. Because if it was wrong, then I'd have to re-record this lecture next hour, and we're not going to record and put online me just doing math wrong. Well, yeah, if you're gone, you can always watch it. There's a notes folder in Schoology. This is gold 3 carbonate. A little harder, plus, first off, bigger number, because gold is huge. What's gold's molar mass? Carbon we already went over is 12.01. And distribute that 3. So there's 3 of them. I'm just going to do that step right away this time. Oxygen? 16. It's 15.999, so it's 16.00, so say 16. And Max, you're correct. There is 9 of them total. Treat this parentheses just like a math class. When you distribute, you had to multiply 3 times 3. Because if I had 3 carbonates, ladies and gentlemen, you can see I have 9 total oxygens. So I need to multiply that by 9. Now, I'll let you do that kind of step on your own, and then you add it all together. That's your molar mass. So what I'd like to do is let's give you, first off, and again, if you want to break up into groups, whatever, that's fine. Let's give you 5 minutes just to practice the front side of molar mass. Then no matter where you're at, you're going to flip to the back side and start doing the mole conversion problems. So again, hopefully that one we got 575.97 grams per mole after we multiplied our gold by 2 as well. So 573.97. On the top of the Lewis Loop activity sheet is once again an explanation on how to do this. I'm going to skip all the way to the bottom where it says in italics, your instructor will show you an example of how to do this on the board for sodium peroxide. In order to do the Lewis dot, we have to know the formula. So we have to know how many of each element there is. Sodium is Na. It's a +1 charge. Now peroxide, it does end in "ide," which makes you think, look on the periodic table. However, there is no peroxin or anything like that on there, so this is a polyatomic ion. O2, and what's the charge on O2? -2. So what's the formula of sodium peroxide? Na2O2, right? This on its own is unusual. Because what I've told you in the past is if you have an ionic compound that has the same subscripts, you should simplify. However, you cannot change the formula of a polyatomic ion. And really what I have is 1 O2 and 2 NAs balancing out. So Na2O2 is the correct formula. Because if we did NaO, it would no longer be peroxide. Heck, it wouldn't even be sodium oxide at that point because it wouldn't balance. So, if we're doing the Lewis dot, on the bottom of your sheet, write down that formula, Na2O2. Starting elements. Again, when we get to this level, no longer just try to draw out your answer, because it's not going to work most of the time. Na has 1 valence electron. I'm going to draw 2 of them. Oxygen has 6. I'm also going to draw 2 of those. This is unusual because if you're doing Lewis dot for something with a polyatomic ion, the nonmetals are going to covalently bond together. But then there's also ionic bonding that occurs with this, because what's going to hold the metal to the nonmetals is an ionic bond. That's why this is the last Lewis dot that we do, is it's a combination of both Lewis dots that we've done. When I do this type of problem, I do it in this order. And what I mean by that is I'm first going to create a covalent bond. Covalent bonds occur between nonmetals. I have 2 oxygens here. So what I'm going to do to begin with is I'm going to bond the 2 of them together. Okay? So I'm going to take this lone electron, because remember, lone electrons pair up, and this one. And there is my bond. Okay? The reason things bond, ionically, covalently, both, is to get to the stable octet. Is oxygen at the octet right now? No. It's at 2, 4, 6, 7. It's 1 shy. Now, some people would say, well, let's do another bond. And you could. But then you're not making Na2O2, you're making diatomic oxygen, O2. And then the NAs aren't connected. And when we give you the formula of something, it all has to be connected somehow. Step 2. ionic bonding. In an ionic bond, metals give to nonmetals. Na can give an electron to this oxygen. If it does that, that oxygen's at the octet now. Right? Second Na, the reason why we have to have two of them, can give to this one. It'll be at the octet. So if I were to draw a final answer for this, oxygen was single bonded to the other oxygen. And I'm not making up my number of electrons here. Why did I put 6 additional dots around each oxygen? Because there is 1, 2, 3, 4, 5, and the 6th that was gained from the sodium. And this is where, again, if we had more time, we'd be doing this at the lab bench, because too often students just start, now let's throw some more electrons at it to make it work. We can't do that. How many electrons total did these two O's gain? 2, right? This is a -2 charge. That's why peroxide is a -2 charge. It's in order to be stable at the octet, it had to gain 2 electrons. Now, let's not forget that we have 2 Na pluses as well. I'm kind of thinking maybe I should just do another one instead of, again, having you guys even try, because, you know, we're at 7 minutes. We're definitely not going to break out and work wherever, because we won't have time then to come back. So, on the back side of this one, let's do the next one on the sheet, which is sodium cyanide. I'd like to give you 30 seconds right now to figure out the formula for sodium cyanide. NaCN. Okay, draw it out. Na has 1 electron. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Again, I'm going to use different colors to kind of help show the steps. Step number 1, covalent bonding. Which 2 elements of the 3 here should I draw a line between to show a covalent bond? The C and the N, carbon and the nitrogen, the 2 nonmetals. Remember, that line now means there's 2 electrons that can be shared between the carbon and the nitrogen in order to get it to the octet. Sodium can give. However, if sodium gave right now, neither the carbon nor the nitrogen would be at the octet. Let's do a second bond. Two, 4, 6, 7. Ooh, nitrogen's 1 away, and I have 1 in my back pocket here with sodium, so that could work. 2, 4, 5, 6 for carbon, though. Double bonding isn't enough. Triple bond. Nitrogen would be at 2, 4, 6, 7, 8, octet. Carbon would be 1 shy, which is where the sodium comes in to save the day. Step 2, when you've done what you can with bonding, now have a metal give. My final answer for this one would be sodium with a plus charge. Carbon is triple bonded to nitrogen, and nitrogen still has a pair of electrons on it. Since it gained, so does carbon. Since there is a gaining of 1 electron, it's a -1 charge. What holds the carbon to the nitrogen? A triple bond. What holds the sodium to the cyanide? An ionic bond. It's both types of bonding all in one. Let's do one more. Barium hydroxide. BaOH2. Now, this one's a little bit trickier, and why I wanted to end with this. First off, barium has 2 valence electrons. Okay, I've shown all my elements. 1 barium, 2 oxygens, and 2 hydrogens. Okay. Gotta get all of our attentions here for a second. When it says 2 OHs, that means you are going to be making 2 separate OHs. And why that's important is some people will first bond the O's together like we've done earlier. And then they'll bond to the H's, and then they'll have nothing left to bond. It won't work. When it's 2 OHs, I need to make 2 separate OHs. So the first thing I'm going to do is bond the O to the H. Hydrogen with 1 bond is stable, noble gas configuration. Oxygen is at 2, 4, 6, 7. It is 1 shy. The metal then comes and saves the day. It gives, and it gives. So my final answer for this one, that barium is a +2. Oxygen bonded to hydrogen. Remember, this is a -1 because it gained 1 electron. And then either you could draw a second OH or put a big 2 in front of it like we've done for ionic things in the past.